there are certain rules which we have to follow, or which anybody has to follow, in order to find out the oxidation state or a number of any particular atom in any particular species. The rules are like this. The first rule is, if an element is present in free or uncombined state, it is given zero oxidation number. Let us see the examples like hydrogen, chlorine, nitrogen, sulfur, oxygen. Like all these are given zero oxidation state. Even in fact, like metals like sodium, magnesium, potassium, etc. Whenever they are present in free or an uncombined state, they all are given zero oxidation state. Second rule, if the ion is made up of only one atom, the charge of the ion is said to be its oxidation state and number. Let us take the examples for this. The examples are alkali metals. In alkali metals, since they all have only one valence electron, they all will be existing in their Li plus, Na plus, K plus, Rb plus and Cs plus states. They all are given +1 oxidation number. Similarly, alkaline earth metals, beryllium 2 plus, Mg 2 plus, Ca2 plus, Sr2 plus and Ba2 plus. All of these, since exist in their +2 +2 oxidations, +2 +2 states, they all are given +2 as their oxidation number. Because they have only two valence electrons, both are lost. They attain this through a noble gas configuration of the previous period and become very stable. So they all are given this fixed oxidation state. Similarly, O2 minus, which is called oxide, is given -2. If we have aluminium 3 plus, it is +3. If we have chromium +3, it is +3. If we have ferric +3, it is +3. So like this, in whatever is the charge which is present and the ion is only made up of one of the atom, its charge is simply said to be its oxidation number. Next rule is oxygen when present as oxide ion, that means O2 minus, is given -2 oxidation number. But we have exceptions to this, like the first exception is of peroxide ions. Peroxide ions here, the ions of oxygen, which oxygen is present as O2 2 minus. We have examples like sodium peroxide, strontium peroxide, barium peroxide, hydrogen peroxide. In all these, it is given oxygen has -1 oxidation number. -1. It is, I think you all are knowing, this is what is exactly the structure of the peroxide ion. O single bonded O, and there are 2 bonds which are to be made. If they are not there, it will be with the 2 lone pairs, 2 negative charges. So each one oxygen atom is gaining only 1 electron. Together, both of these are gaining 2 electrons. That is why we have O2 2 minus. So it's only the -1 oxidation state which is there in case of peroxide ions. The other is your superoxide ion. O2 single minus. Example, potassium superoxide, rubidium superoxide, cesium superoxide. In all this, oxygen is given -1/2 oxidation number. -1/2, because 2 oxygen atoms are in gain of only 1 electron. So 1 will be in gain of only half of electron. So actually the oxidation number is -1/2. It's -1/2. But there are other examples of oxygen also, like oxyfluorides. When I say oxyfluoride, it means it's compounds with fluorine, in which fluorine is present in the negative, as a negative ion. We have 2 examples, OF2, O2F2, in which we can clearly find out here it is existing in +2 state, it is existing in +1. So in oxyfluoride, oxygen is either +1 or +2 oxidation number. The next rule is regarding hydrogen. Hydrogen is given +1 oxidation state, because generally it loses 1 electron and is present always in the form of H+ ion. But there are exceptions to this, which generally can be classified as ionic hydrides. Hydrides are the molecules or the compounds of hydrogen in which hydrogen is present in the negative state, is present as an anion as a negative state. Generally, ionic hydrides, since they are, as the name shows, they will be ionic in nature, are formed by the metals of group 1 and group 2, because they are most electropositive. We can take the example of lithium hydride, sodium hydride, potassium hydride, calcium hydride, which is also called hydrolith, magnesium hydride, etc. In all these examples, remember, hydrogen is present in the -1 state. So it is given, hydrogen is given -1 oxidation state in case of ionic hydrides, else it is always given +1 oxidation number or state. The next rule is regarding halogens. Halogens, it's fluorine, chlorine, bromine and iodine. We already know them. They all are very strongly electronegative in nature. They always accept electrons and are present in their -1 states. They are always present in the negative states. So remember, in this, fluorine is given a fixed -1 oxidation number. This is fixed because it never shows any other state, positive or whatever it is, except -1, or whenever it is present in the form of F2 molecule, then it is given a 0 state. Otherwise, since it is the most electronegative species or substance, it is always given -1 state or number. But this chlorine, bromine and iodine, though they are generally given -1 oxidation number, but we have exceptions. The first exception is of their oxides. Oxides of chlorine, bromine and iodine. Let us take Cl2O, Cl2O3, Cl2O5, Br2O3, I2O5, etc. In all these states, chlorine, bromine and iodine can exist in their +1, +3, +5 or even +7 oxidation number. It depends on with how many oxygen atoms they are combining, and according to that, then they can lose the number of electrons. So they can exist in positive states in the form of positive ions or ionic species in the positive states whenever they are combining with the oxygen. So oxides of chlorine, bromine and iodine are having them in their positive states. Whereas we have done just now, whenever fluorine combines with oxygen, fluorine is always in minus state, -1, because fluorine being more electronegative than oxygen always forms oxyfluorides rather than fluorooxides. Another example we have, which is an exception to this, interhalogen compounds. Interhalogen compounds are those compounds which halogen forms with themselves. Whenever they combine with each other, they form these type of compounds. We can have the examples like ICl3, IF5, ClF3, IF7, BRF5, etc. What is important to note in this case is always the smaller halogen will be in -1 oxidation state. And I think you all know their sizes varies like this. Let me rub out this for you. The smallest is your fluorine. This is their atomic size. Then chlorine, then bromine, and then iodine. So the smaller halogen will always be in the -1 oxidation state or number, whereas the bigger halogen will be in positive oxidation number, which can be positive +1 or +3 or +5, or it can be +7. Like we have seen in IF7, iodine is in +7, fluorine is in -1. BRF5, it is in plus, bromine is in +5, fluorine is in -1. Iodine +5, in IF5, iodine is in +5, fluorine is in -1. In ICl3, this is in, iodine is in +3, chlorine is in -1. So these are the interhalogen compounds, and in which we have bigger halogens combining with the smaller ones and existing in the positive states. The last rule says that the sum of the oxidation number of all the atoms of the molecular species must be equal to the charge of the molecular species. If the species is neutral, the sum is equated to 0. Now let us understand all these rules by taking certain examples. Like, let us take example of K2MnO4, which is called potassium manganate. It's, since the molecular species is neutral, it's not having any charge, we will have to find out how many the electron the manganese will be losing, because as per the rules we already know, since potassium is an alkali, it will be existing in the +1 number. Since it is the normal oxygen or normal compound of the oxygen will be present in the form of its oxide, so it will be in -2. So we will be eager to know how many electrons this manganese atom in this molecular species has lost or gained. So let us do it like this. There are how many potassium here? 2 potassium. So we will take 2 multiplied by +1, because this +1 is for your potassium, and since there are 2 potassium, we will multiply this by +1, plus, since this manganese which is taken as X, so we will take X as the oxidation number of manganese, plus how many oxygens we have? 4. All 4 are in -2 state, and since the charge is not there on there is no charge on this molecular species, it is equated to 0. When we solve this, we find that manganese is present in +6 state. It's 4 2s are 8, -8 comes here, and 2, it will be +6. So it means manganese is in +6 state or number, and it has lost 6 electrons in this particular molecular species. Let us take some more examples. I hope it is very much clear to you from this example. Let us take example of a very simple sulfate ion. In this, oxygen as usual will be in its -2 state. Sulfur is not, we are not knowing how many electrons the sulfur has lost. So let us take this to be existing in the form of X oxidation number. So how we will find out? X for sulfur plus 4 for oxygen, each in -2 state, equal to -2. It's 4 2s are 8. It comes out to be +6. It means sulfur here is present in the +6 oxidation number. Similarly, let us take example of MnO4 minus ion. in this MnO4 minus ion, a manganese oxidation number is to be determined. Let us take it to be existing in the X number. There are 4 oxygen all in -2, and since the charge is -1, it is -1. This comes out to be +7. So manganese in this ion is in +7 state. Manganese here, this particular ion is called permanganate ion. This is called permanganate ion. Let us take the example of Cr2O7 2-. This is called a dichromate ion. In this, we want to find out in which state or what is the number of electrons the chromium has lost or gained. Now let us take it to be an X. So it will be twice of X because there are 2 chromium atoms and there are 7 oxygen all in -2 state, equal to your -2. So it is 2x minus 14 equal to -2. There are 7 oxygen all in -2, remember, and I have equated with the charge which is there on the molecular species. So it is 7 to the 14 minus 2 this. So this will make twice of x equal to 12, and this will come out to be +6. So how many electrons this chromium is losing? 6 electrons. So this is how we can find out how many electrons any particular atom in any particular species has lost or is in gain by finding out its oxidation number by following these all simple rules.